In this lab, I will be analyzing the motion of an object with a non-negligible amount of air resistance falling. In this case, I will be using Newton's second law to test if the results were correct and if Newton's law can be used in cases like these. I'll be using a sponge as it has a lot of air resistance, and will be analyzing the motion of it falling. Newton's second law states that the final velocity is equal to the initial velocity plus the net force over the mass times delta t. I will be using Newton's second law in this lab to find the net force on the sponge and predict the new velocities of the sponge. The weight of the dry sponge I am using is about 14.4 grams, or 0.0144 kilograms, which is the measurement that will be used in calculations. Now, let's analyze the observations of the sponge in motion on track. During the test, the sponge is traveling in the negative y direction since it is falling down. I had to also make sure I chose a time span from where the sponge was dropped precisely to where it is falling. As you can see from the points in tracker, the velocity is definitely not constant, as it is sloping downward at an increasing rate. From Newton's law, we know that this means there must be some net force acting on the object. Since the sponge is in free fall, the only forces acting on it are the force of air resistance and the force of gravity towards the center of the Earth. The force of air resistance on the sponge is proportional to the velocity squared, or equal to negative b times v squared. In order to see what Newton's law would have predicted without any human error, yet with included forces acting on the sponge, I made a program in Python to create an exact model. Let's take a look. First, I made a program to see what would be predicted if there were no air resistance acting on the sponge, and only gravity. I input the initial velocity vector as 0 meters per second, since I started to analyze the motion at 0 velocity. The net force in this situation will only be the force on the sponge due to gravity from the Earth, which is about 9.8 meters per second squared toward the center of the Earth. I set the constant g equal to 9.8, which is the magnitude of the gravitational field. I also chose a delta t of 0.0025. Since my video is only about 0.3 seconds long, I needed a very small delta t in order to make this model precise and accurate. My initial position at 0.003 and 0. I also had to include a unit vector so that later I could define the weight force in vector form. I had the negative mass of the ball times gravity times the unit vector in order to get a vector of the weight of the ball. I then put the weight force equal to F net, and then I included Newton's second law into this program, and it will go through this loop until t is equal to 0.368 seconds. Let's see what the results are. Once the model is run, we can see that it has the same type of motion with an increasing downward velocity. The ending position in mine is about negative 0.59 meters, while the ending position in my Python model is about negative 0.67 meters. Let's see if including air resistance will fix this. To do this, I need to add an air resistance force. The equation to find the air resistance is that the force of the air resistance is equal to negative b, some constant, times velocity squared. In order to find b, I had to plug in different values of b and pretty much guess and check until I found a value that would lead to the same ending position in my graph. Here, my b constant is equal to 0.01. I had to include the force in my code, b times the magnitude of the ball's velocity times the ball's velocity in order to get it back into vector form. I then put this in the net force equation. The graph looks about the same as the one that I have in Tracker. For this model, you can see that the ending position is about negative 0.588 meters in the y direction. And in my model, the ending position is about negative 0.59 meters in the y direction. Let's see how well these models matched my observed results. In this Excel spreadsheet of the results, the red line is the model without air resistance, the blue line is the model with air resistance included, and the green triangles are the points of my observations in Tracker. For the most part, the observed points and the model without gravity match up until the end, when the model starts to fall at a steeper rate. A model where air resistance is counted in matches quite consistently with my observed results. This is because the sponge did have some non-negligible amount of air resistance against it that needs to be accounted for in the Python model. Terminal velocity occurs earlier for something with more air resistance. Here you can see that the slope of the blue line and of my green triangles is evening out a lot earlier than the red one looks like it will. Once the slope evens out, that means that the object has reached terminal velocity, since it is traveling at constant velocity. Also, if my sponge were initially thrown downward, it would just make all of these models start at a different place, but it would not change the overall shape of the curve. Thus, Newton's second law justifies the motion of a falling object once again, and helps put the importance of air resistance and net forces into play.